Okay, we are recording. Let me just check the levels. Yeah, okay, good. Okay, so here's where we were last time. We were talking about partial derivatives. So keep in mind the idea of a partial derivative. It's a foot in the door. It's a first kind of attempt to make a reasonable idea of what a multivariable derivative ought to be. It's pretty clumsy if you get right down to it. The big idea is if you have a function of three variables like we have here, this is a function of x, y, and z. Let's just pretend that it's not, right? It's kind of silly, but we're going to just pretend that because we're taking a partial with respect to y here, we're going to pretend that x and z are constant and therefore that all of this is constant. And so we're really only taking the partial derivative, well, we're only taking the derivative, if you will, of this function of a single variable, which is constant times y squared, and that's easy. Right? So it's a foot in the door. It's something. It has some uses here and there. It has a lot of nice features. It's very easy to compute. You got to love that part of it, right? So that's great. And we saw several more examples last time. I also started in on the idea of geometric interpretations. By the way, good general rule of thumb in math: if you make a definition, you have the advantage that you get to define whatever you want, right? The cost of that freedom to define whatever you want is that no one's going to be interested in what you just defined unless you make it make sense somehow, right? So you got to give some, like, does it look like something geometrically natural? Does it relate to some sort of a physical quantity in some way? Or are we just writing down nonsense, right? So the first satisfaction that we get on this is by looking at the graph context, right? Keep in mind what a graph is. A graph is the picture that you get by forming the equation where you set the value of the function equal to a new variable. So in that specific context, we went through and thought about, okay, well, how do you compute a partial derivative and what do those steps look like as we go through that process? What do they look like geometrically? And I won't repeat all that, but the punchline was that if you're taking a partial derivative with respect to y, then the idea is we're going to look in the y direction. We're going to take a vertical cross-section in that y direction. Notice that means that x is staying constant. Okay? That cross-section will be a curve, which is effectively the graph of the single variable function that we're kind of assuming that we're dealing with, right? And so the derivative then is just the slope of the tangent line, right? So that was our nice conclusion. We love this conclusion for a couple of reasons. For one thing, it's geometrically simple, right? It directly relates to one of our favorite pictures of how to visualize a function. It's a very simple idea, namely that of a slope, right? Very geometrically natural. And then also, of course, very familiar. This is, we were fingers crossed throughout this whole process. Oh gosh, this is a derivative. I hope it looks like derivatives used to look back in Calc 1, right? And we kind of got our wish in some sense. Okay, so that's all nice. And that's where we finished last time. Wait, is it? Wait, did we get through? I can't remember. Did we do this stuff here? I don't think we did. Okay, all right, good. So that's where we left off last time. And now here's where we really have to kind of broaden our minds a little bit, right? If you have a function of several variables, such as this one here. Here I have a function of three variables, right? And notice now that I have a different kind of a picture here. This is not a graph. I can't draw the graph of this function, R3 to R1. It's a four-dimensional picture. I couldn't even begin to. But I can draw this literal picture where I literally draw the domain over there. I literally draw the target over here. They are Euclidean spaces. I draw them, right? Could not be more literal than that. How would I understand the partial derivative with respect to y in this context? Right? Not on a graph. It's not a graph. I can't say slope because slope of what? There is no picture. There is no surface. Right? So slope just doesn't make any sense at all. So what is a partial derivative in this context? And the big idea here is keep in mind that if y is your variable, that means that x and z are constants. And so we're going to fix x and z. There's the line that you get when you insist that x and z both be constant. Neither x nor z is allowed to change, so you're really only allowed to move just in this one direction. And here's the interpretation I'm going to give you of this y partial. Partial derivative with respect to y, again, it's a relationship between input changes and output changes. And this is going to be a familiar, I hope, interpretation from Calc 1. In Calc 1, one of our alternative interpretations of a derivative is, well, if you've got some input change, you change the input by some amount, and you want to know correspondingly how much does the output change. Right? The relationship between input changes and output changes, that's what a derivative is. Right? So this partial derivative with respect to y, it's not really a geometric thing on this picture. It's not a slope, it's not a length or a volume or anything like that, right? But it's a relationship between things that I can draw a picture of. Like the relationship between input change and output change. It's the thing you multiply by the input change to get the output change, which is a sort of a relationship. Everybody with me? So, again, I've said it before, I'll say it again, I emphasize, it's not a slope, right? And this is a nice example, I think, sort of our first example of how calculus looks different in different kinds of pictures. If you're looking at a graph picture, then you have one interpretation of a derivative. If you're looking at a totally differently constructed picture, then no surprise, you get a totally different kind of a picture. Okay. All right. What if we're looking at level sets? Different picture. Again, so we should not expect what partial derivatives look like in this context to necessarily have anything to do with the previous two interpretations that we took, right? And this is going to be another one that's kind of different. A lot of people, here, the common mistake that so many students make is to say, oh, well, let's see here. So at this point, if I want to take a partial, well, partial derivatives are slopes, so I guess it must be this slope right here. Wildly wrong. This is an interpretation intended for graphs. This is not a graph. Right? So again, please don't make that mistake. Don't step on that landmine. You have to be actively, consciously on the lookout for making sure that you're thinking about what kind of a picture is this before you start making geometric interpretations of things. Okay, all right. So, let's think about how we do interpret level sets. Reminder, my favorite example of level sets, contour lines on topographical maps. Right? Which again, if you want to see some examples, you can. It's as simple as going to Google Maps, and you got to click on, I think it's called terrain or something, and then as you zoom in, there's a certain level where they will show the contour lines. Anyway, as we previously discussed, if you were at this point, and if you were to take off and start moving in the x direction, that's a pretty steep hike. Look how close together these contour lines are, right? I'm crossing from one contour line to the next contour line in just a teeny tiny little bit of horizontal distance. So that's looking kind of steep. That is, if I were looking at the graph, which I'm not, but if I were looking at the graph, I feel like I'd be going up a lot per unit horizontal distance in this direction, in that x direction. So I feel like this would be steep. And steep means a high value of the partial derivative. Right, now related question. Let's think about what happens if I move in the y direction. Well, as I move in the y direction, we can play the same sort of a game. I'm still crossing contour lines. But notice, rather than taking a teeny tiny little bit of horizontal distance to cross two contour lines, here I have to cover quite a bit more horizontal distance. Right? And by the way, keep in mind, this looks like up. It's not up. That's north, if you will. Right? It's still horizontal. Right? So much more horizontal distance to cover, well, to gain the same amount of altitude. That seems less steep. That corresponds to a smaller value of the partial derivative. Everybody see what I'm talking about? Now, there is something very unsatisfying about this. In the picture, I can't really quantify this, right? There's, how do I get a sense of scale here? I guess if I were going to try to get a sense of scale from this kind of a picture, I'd really have to do more labeling. I'd need to know altitude-wise or value of the function-wise how far apart are these lines. It's not indicated on this picture, so I can't get that sense of scale. Likewise, how far are these distances? Is this a map of the entire continental U.S., or is this a map of, my property at my house? So that sense of scale would also need to be there. So this picture is kind of just not that good for getting that sense of scale. What it is really good for is making relative arguments. So at a glance, no scale required, I can see that this green direction is steeper than the blue direction. That's just a snap. Perfectly clear. Everybody happy with that? So again, pros and cons, right? It's not, we don't get all the information in all the pictures. All righty, moving along. Okay, so next thing we're going to do, kind of a nice application of partial derivatives. Let's talk about something called linear approximations. And just real quick, I don't want to go off on a digression, but technically the functions we're about to write down are not actually linear. And since y'all have had classes in linear algebra, you're going to notice this pretty much right off. They are not linear. They are what's called affine, if you care. You don't have to. You're not going to be tested on that term, but just a cultural point. So I'll get in a minute, well, in several minutes, I'll get to why we use the term linear approximations. There is a good reason. But anyway, here we go. Before, though, I can actually get started, one other thing I need to note. There are some really sticky, subtle, deep questions that go into what I have circled in red here. That, how do I even know that a linear approximation exists? This question is much nastier in multivariable calculus than it is in single variable calculus. Single variable is pretty simple. If you can take a derivative, then it's differentiable. And if it's differentiable, then there's a linear approximation. And these things are all just kind of the same, different phrasings, different choice of words, but the same ideas. Not so in multivariable calculus. Again, deep, sticky, nasty questions are underneath, and I'm gonna give you some idea of what I'm talking about there in a few minutes. For the moment, again, I don't want to get bogged down in the ugly technicalities, so I'm going to, for the moment, assume that everything's nice, that the linear approximation exists. And then ask, okay, yeah, how do I do it? What's the formula? How do we get this done, right? And then in a few minutes, I'll talk about worries and how to avoid them. Okay. All right. So linear approximation, old idea. Different point of view you can take in single variable calculus on how to do a linear approximation. Notice my first example here, single variable function. My favorite point of view on linear approximations is it's a degree 1 polynomial that agrees with the function that you're approximating in value and derivative. So it mimics, it copycats the function that we're trying to approximate, both in terms of the value it takes and the derivative that it has at that given point. And I know y'all have all done your Calc 1 previously, long ago probably, but a reminder that this is the answer in Calc 1. If you have if the linear approximation exists, then that's the formula that we've all seen before, I hope. Okay, now I'm going to leave it as an exercise to y'all. You may have already done this exercise, but I think this is a healthy exercise if you haven't done it or if it's been too long and you don't remember how to do it. confirm for yourself that this function here is the one that has not only the same value, but also the same first derivative as the function f that it allegedly approximates. It's just a matter of writing it down, right? Just plug in what L of A is. Just plug in x equals A. See what you get, right? Take the derivative and then plug in x equals A again. Confirm this. So make sure you can do that. If you have trouble, something goes a little wrong, you're not sure what the problem is, come to my office hours. We're very happy to help you out. Okay. All right, so the big idea then, this being a multivariable calculus class, we're going to kind of rip off this same concept. And I'm going to define a linear approximation of a multivariable function. Here we go, multivariable function here. Whoa, pen slipped there. Multivariable function. By the way, momentarily, real valued only. Real valued only. We'll get to the vector valued in a few minutes. Real valued multivariable function. The linear approximation is computed with this formula. And again, I'm going to leave it to y'all as a nice exercise. I think this is good mathematical weightlifting. Confirm for yourself that this function that I have in green has the same value as f when you plug in x equals a. And furthermore, that it has, let's see here, we would have said the same derivative, but wait a minute, this is a function of several variables. There's a bunch of partial derivatives, and I claim this has all of the same partial derivatives as f at point A. The way you're going to confirm this, items 1 and 2 here, again, exercise for y'all to do on your own. You're going to totally copy what you did back here. Adapt it appropriately, right? But it's a really, really analogous. The one that I feel sure you've either done before, you've seen it done before, that hopefully you should have no trouble with. And this brand new one, they're morally kind of the same calculation. Everybody see what I want you to do? Okay. All right. So one thing you'll notice about this formula here, it's kind of big and clunky. And that's it gets a little old writing that all down. It takes so much time to write it all down. So there is a really nice simplification here. Notice in this formula, all of these terms kind of look alike. Notice also these terms that all kind of look alike, they are all products of partial derivatives with differentials, you might call them. Right? The first coordinate, we were looking at at a point whose first coordinate was a1. Then we moved over to x, whose first coordinate is x1. Okay? So that's a differential. And then you look at this and you say, okay, well, I have a sum of a bunch of terms. The terms all look alike. Each one is a product of two factors. My gosh, this purple expression here is a dot product. I mean, just structurally, it looks just like a dot product. So the big idea here, let's see if I can squeeze all that. Yeah, this will all fit. Big idea is to say, all right, well, I'm going to write it as a dot product. This is what we're about to turn it into. What I have in orange here, all of these orange terms together, is literally just the coordinates of the vector x minus a. So, okay, again, what do we have here? Not only is it a dot product, it's a dot product where one of the factors is natural. X minus a literally represents the differential of, well, I was at the vector a, now I have moved to the vector x, and that difference represents how much did I move in the input. So in a circumstance like this one, where an expression that we know is interesting, we know this expression up here is natural, because this is how we write linear approximations. And it can be written in terms of two things, one of which we know is natural. that unavoidably makes the other natural. This thing right here, this vector whose coordinates, whose components are these various partials, this is the thing that naturally, by way of dot product, relates the natural input differential to the natural output differential. So this thing in green does something really natural. Well, if you have something that does something really natural, it deserves a name and a notation and such. And here it is, the this notation that we use is right here. By the way, we call this thing the gradient of a function. We use this symbol here. It's kind of an upside down triangle, if you will. By the way, very importantly, not a right side up triangle. The point goes down. It has to go down. If the point goes up, it's a different thing. Capital delta, right, with the point going up, different mathematical object. Actually, it's a couple of different mathematical objects, but very importantly, this one goes down, not up. So we call it the gradient. We're going to learn more about the gradient later on. For the moment, though, this is just, it serves the purpose of allowing us to rewrite something big and bulky as something much more compact and convenient. So for the moment, the gradient is just a convenient shorthand, and that's all. Is that cool? Everybody happy? All right, so in practice, day in and day out, this is how people write linear approximations right here. And that's the formula that I encourage you to make sure that you know. Let's get our hands dirty with a quick one here. How do we compute the linear approximation of this function at that point? And this is totally plugging in and just kind of writing a few things down. This is very direct. So we are interested in this point, 1, 2. That's going to be our A. Let's see here. We're interested in this function, f. Apparently, I'm going to need to know what the gradient of that function f is. Gradient, well, I have a formula up here that says the gradient is just all the partial derivatives sort of compiled together as a vector. So, okay, let's do that. Here's those partial derivatives. Now, notice the formula specifically says that I need to plug in for the gradient, right? I don't want to leave the gradient as a function of x and y. I need to know what is the gradient at my given point 1, 2. So notice I am literally plugging that point into there as indicated like that. And then this then is my gradient evaluated at the given point. So the evaluated gradient, 2, 4, and notice it just goes right there where the formula says it's supposed to go. Anybody happy? That gets multiplied by, let's see here, dot producted with, that is, x minus a. Notice there's x minus a. And again, you can explicitly see the a as the 1, 2 that I'm subtracting from x, y. Is everybody happy? Plug and chug. Okay. And of course, you got to evaluate the function itself, and the function itself, you plug in the point, and that works out to be 5. So there's your answer. There's your linear approximation. Totally plug and chug. Now, I've done one additional thing here, you'll notice. And I rewrote this expression as this simplified expression down here. I put that in there just to point out that you could do that, right? I mean, this is literally just algebra. You can crank it out, and there's a tendency to think that, well, yeah, you probably should. If you are going to be using that linear approximation over and over and over again, then that's a good idea. That'll save you time in the long run. If you're going to code it into some program that's going to compute this linear approximation a few billion times, absolutely. right? But for math purposes, case could be made that rewriting this as that kind of just obscures the structure that's visible in this original form that we have here. It's kind of nice to be able to explicitly see the gradient here and to explicitly see the original value of the function there and explicitly see the 1, 2, that's the base point that we're sort of that we're basing all of this at. So, on an exam in this class, unless it specifically says otherwise, honestly, I wouldn't bother with this rewriting down here. It doesn't really serve a purpose for our purposes. Does that make sense to everybody? All right. Okay, now vector-valued functions. What do we do if the function, mind you, still a multivariable function? What if it is no longer real valued, but vector valued? Several outputs. The algebra here gets a little hairier, right? But ultimately, it's kind of a matter of just writing down a formula and directly plugging in and confirming that it has the right derivatives and stuff. It's a matter of just kind of doing it. And rather than give you the full formula and then show you the notational shorthand, I'm going to spare myself, if only myself, but also y'all, the horrors of what that looks like when you write it all down by just going straight to the notational shorthand. And here it is. We're going to make great use of this thing called df. Eventually, we will see cause to call this the derivative matrix. That'll be in just a few minutes. And it is this matrix right here. Formula that you have to just know. It's playing a role kind of like the gradient vector. If you look back to the gradient vector, the gradient was a vector whose entries are the various partial derivatives. There's various different input variables, and so you get one partial derivative for each input variable. Here, this derivative matrix, again, is just an assembling of all of the partial derivatives. It's just that now you can not only take partial derivatives with respect to various different inputs, you also have various different output coordinates. Right? F has F1, F2, F3, the various different coordinates of this vector valued output. So you have more partial derivatives, and thus it ends up being a matrix instead of a vector. Now, it is critical, by the way, that this be organized exactly as is indicated here. Otherwise, it won't do its job. So specifically, the partials with respect to x1 go in the first column. Partials with respect to x2, second column, etc. So I like to think of this then as being this is casual terminology, but the first column, I'll call that the x1 column, because the common feature of all the entries in that column are that you're taking the partials with respect to x1. Likewise for the x2 column, x3 column. Likewise, notice that all of the entries in the first row are partials of f1. So, no surprise, I call this the F1 row for exactly that reason. Does that make sense to everybody? So, important little memory tool to make sure that you remember. This is really, really, really important. Columns correspond to input variables. Rows correspond, in this sense, to output variables. And if you get that switched, then you're going to be all messed up. Is that cool? Is everybody happy? Okay. All right. Now, again, this is an arbitrary seeming formula that I just wrote down here. What's so great about this thing? And the answer is that it's the magic matrix that does what we want it to do. And you can confirm for yourselves that with this magic matrix that we just wrote down, in that position, kind of right where the gradient had been, kind of right where the single variable derivative had been in the single variable linear approximation. This is the thing that makes it all work. This is what makes our linear approximation formula have the right value, and what makes this linear approximation formula have all of the right partial derivatives. And very importantly now, when I say all of the right partial derivatives, I mean with respect to all of the input variables. And furthermore, let's see here, colors, with respect to all of, partial derivatives of all of the same output variables. So all the various partial derivatives, in other words. And again, this is something that y'all can check for yourselves. I encourage you to do this. I totally understand if you don't want to sort of write this all down for in general, n by m. That's a lot of terms and dots, and it'd be easy to get confused. But I think it'd be a really good practice problem, healthy exercise. Think about a function f that has, let's say, 2 input variables and 3 output variables. And then write down exactly what this matrix is. And then expand and write down all the terms. There's only 6 of them. It's not that bad, right? And then confirm, just directly, brute force, confirm that we have all the right values. Well, we have the right value, and we have all of the right partials. There would be 6 partials to check in that case. And frankly, after you do a couple of them, you'll notice the pattern to see how this, it clearly works. Does everybody see what I want you to do there? All right. And again, let's write one down. Multivariable vector-valued function. Point at which I want to do a linear approximation. So, okay, let's play the game. Here's the derivative matrix. That's just a matter of taking a bunch of partial derivatives. Now, remember, you got to be very, very careful about this, right? The rows correspond to to output variables, right? So what we have in the first row, that's the various partials of x squared plus y squared with respect to the 2 different input variables. The columns correspond to input variables. So all of the partials that are in that orange first column, those are all x partials. All of these partials over here, these are all y partials of the various output coordinates. So you can pretty easily confirm, right, that this 2x, well, that's the x partial of x squared plus y squared. And this 2y, that's the y partial of x squared plus y squared. And then, again, healthy exercise. Make sure you, think it through for, the second output, second row, and the, third output, third row. Okay. All right. So various partials to be taken. Again, very careful with the organizing of the derivative matrix. As previously, you got to plug in the point 1, 2 to get your actual evaluated derivative matrix, and it goes right where the formula says it should. And then let's see here. That's this right here. And then x minus a, what you're multiplying that by, notice 1, 2. What we're subtracting from x comma y, 1, 2 being our point where we're doing the evaluating, and etc. So plug in and chug it. Everybody good? All right. A couple of quick observations. We've kind of already made this first observation, but the columns are all partial derivatives with respect to the corresponding input variable. If you think about it then, what that means is this column is the partial derivative with respect to that input variable of the vector-valued function f. It's literally got all the same coordinates that it should as the partial derivative of the vector-valued function. So one way to think about the derivative matrix is that it is that the columns are partial derivatives. And now you can notice at a glance that since each row is the partials of a given output variable, all of the partials of each given output variable, well, all of the partials is what a gradient is. So each one of the rows is a gradient of one of the coordinate functions. All right. The last little quick comment I want to make is about where, again, that term linearity comes from. I previously observed, and I'm sure y'all noticed as we were going through, these linear approximations we write down are linear. It's really frustrating terminology. If the name includes the word linear, don't you feel like the thing should be linear? Right? So it's not, but the main player, the thing that does all of the work in that, is the DF matrix, and being as it is a matrix, it is linear. So that's the motivate. That's why we call it a linear approximation. I guess if you wanted to get real technical about it, we should call it the approximation based on the linear matrix that keeps track of how the function's changing. I don't know. You could throw some words at it, but it gets really clunky. So people just say linear approximation. All right. Okay. We'll talk about tangent lines and tangent planes. Starting with tangent lines, let me remind you about tangent lines. Very common mistake made in single variable calculus classes is to conflate the tangent line and the linear approximation. These are not the same things. I mean, they're really closely related, but they are not the same thing. The point is, one of them is the graph of the other. And remember, I've already given you all the sort of the speech about how you really can't conflate a function with the graph of the function because we're not always looking at graphs. Right? You can get into big trouble this way. So it's annoying, right? But here's your linear approximation. That's that function that we've been talking about. Notice it's a purely algebraic object. It's just a function. That's it. Okay? It does a good thing. It's a function that has nice algebraic features. Good approximation of the function and all that. The tangent line is the graph of the linear approximation. So it's the graph itself of that linear approximation, not the function whose graph we're looking at. Does that make sense? I know it's a fussy distinction, but again, it's really important to make sure you don't conflate different things. Everybody comfortable with that distinction, I hope? We're going to make the exact same distinction now in a multivariable setting. You'll notice I'm drawing here the only graph of a multivariable function that I really can in a situation like this. And that's when you have two inputs and one output. And we've already talked about when you have two inputs, what is the linear approximation, and there's the formula. Notice we use the gradient, right? Shorthand gradient notation, very convenient. That is a function. It's not a plane. But its graph is a plane. And it for all sort of the same reasons that the graph of the single variable linear approximation is a tangent line, likewise, this graph here is the tangent plane. Everybody buy it? One way to think about that geometrically, by the way, is if you look at, how would I persuade you that this plane, this graph of the linear approximation, how would I convince you that that's tangent? Well, keep in mind, we already know that this linear approximation function has all the same partial derivatives. In a graph context, partial derivatives means slopes of cross sections. So this blue plane here and the original graph of the original function, when I take slices in either axis, in either coordinate direction, those slices all have the same slopes as the original graph does. And thus it kind of angled sort of the same way as the original graph. Thus it's tangent. Yes?
The matrix has 2 by 2, so it would be 4 things. But if you slice, you only have them 2.
Say it one more time, I'm sorry.
The matrix has 4 things in it. But if
Oh, wait, are we talking about this picture here?
Yeah.
So the matrix has 2 things in it. So there's 2 input variables, but there's only 1 output variable. Right? So if you were to write and you could, by the way, write this, I'm writing it as dot product with the gradient, but you could write it as matrix df, right? Matrix vector multiplied by x minus a. That's also fine. But yeah, that matrix would only have 2 entries. Yeah. Is everybody happy? In this case, it's a lot easier to write it as a vector dot product. I say a lot. I mean, it's. I should amend that. It's, I think, easier. But it's equivalent. Okay, moving along. So now these next 3 pages are going to be a quick exploration into the deep water that I claim we just kind of windsurfed right over, right? I just need you to know that there's scary monsters down there. Right? I don't need us to actually do battle with the scary monsters. Right? So I just want to show you the kind of things that we need to be worried about, and roughly speaking, how math treats these situations. And then we're just going to kind of move on. So again, I don't want to get too bogged down in any of this stuff. But you recall the very first thing I said when we started linear approximations is I assumed that the linear approximation exists. I just assumed it. Now let's sort of return and do our, we have to kind of, readdress that question. Okay, I wrote down a formula. Is it really what I claim it is? And I just want us to recognize it might not be. There's a pretty easy example here where it fails. And here it is. It's kind of a strange function. Oh, sorry, circled the wrong. There we go. A little bit of a strange function. It's not the typical sort of algebraic formula that we're accustomed to, but I'm going to define this function to be 1 if either of the input coordinates is 0, right? And it's going to be 0 everywhere else. So in particular, now I can draw a picture of this. 1 if either x or y is 0 means above the axes, the value of the function is 1. So plotting that part of the graph, above the axes, the value of the function is 1. So it's lifted 1 above the xy plane, if you will. And everywhere else, the value of the function is 0. Let's see here. I guess I'll use green for this. It's 0 everywhere else. So the value of the function is 0 kind of over there, and is 0 over here, and over there is all 0, and etc. Everybody kind of see what this function looks like? It's a weird graph. Highly discontinuous, right? Okay, so let's take this function. Let's write down the formula that we just wrote down for what for how to find a linear approximation. Let's just assume that it exists like we had done previously. And in order to find the linear approximation, well, I'm going to have to take the value of the function at the origin, which is 1, right? And then I've got to take the gradient. Now, wait a second. Let's think this through. What is the gradient? Keep in mind the gradient's made up of partial derivatives. The first coordinate of the gradient, then, is the partial with respect to my first variable. I need to compute the partial derivative of this weirdo with respect to x. I'm not going to be able to do that with formulas because this isn't a formula kind of a function. But I can look at the picture and see that's really no problem. If I want to look at how the function is changing when I'm at the origin, as I move in the x direction, the value of the function, it's not changing at all as I move in the x direction. That's constant as I move exactly in the x direction. So this first partial derivative is 0. And likewise, this second partial derivative, as I move in the y direction from the origin, still the value of the function is constant and thus 0. And so if you take all this and put it together, the linear approximation would be just a constant value 1. And if I were to try to draw that picture, it would be something kind of like this. It's a plane here that has constant height 1. Oh gosh. I'm just trying. Okay, there we go. Constant height 1, sitting above the xy plane. Everybody see that? Is this a good linear approximation? I say no. I say this is terrible. This is sufficiently bad that I don't think linear approximation is I don't think this is in any sense a reasonable approximation. So now I'm going to erase all my picture here because I need to highlight something more specific. Let's get rid of all the mess. And let's think now about what happens as I approach the origin at an angle. Right? As I approach the origin at an angle, well, the value of the function is 0 for all of those points. Right, but the value of the linear approximation, we just got through agreeing, the value of the linear approximation is 1 for all of those points. So are these red numbers doing a good approximation of these yellow numbers? Not even remotely. That make sense? Yeah.
How are we geometrically defining good?
Yeah, exactly. No, that's right. We're going to have to work up to that. Yeah. So how to be precise about what I'm saying is something we're working up to. I'm just going to make an appeal right here. Whatever definition of good we come up with, it better not include this, right? Because that's clearly bad. Yeah, right. Very good question, but that's going to take us a while to get there. Okay. Now, look, one take you can make on the problem here, a very simple, reasonable take, is that let's look at how far we're off, right? What's the error? What I'm highlighting in blue here is the difference between the approximated value and the actual value. So the error doesn't even approach 0. Well, that's bad. How about this? How about we just say, look, I need that error. Right? This error, maybe I should just require that the error approach 0. That would eliminate this as a possible, linear approximation. This requirement that the error approach 0 would say this is clearly not a good linear approximation. And a lot of students, when they're sort of first getting started, are tempted by this idea that, look, error is the bad guy. If the error goes away, isn't that a win? Right? It's very tempting to think that, hey, no error, no problem. And it's not good enough. It's really not. Check this out. Different example, but perfectly innocent example here. F of x equals 5. It's just nice single variable even. There's the graph of my actual function. And now let's look at this candidate linear approximation, 3x. Looks like that. Anybody willing to believe that this is a good tangent line to the green line? No, of course not. That's ridiculous. It's just nonsense, right? And yet, if you look at the error, right, the error being the difference between the right value and the approximated value. Well, that error, being that difference, does approach 0, and you can see it right here in the graph. Right? So if we use this as our standard, that, no error, no problem. then we would be forced to accept this red line as being a tangent line to this green line. And again, nonsense. There's no way that this is the definition we want. Everybody cool? Okay, so we have to get weirder about this. We have to get fussier. And I'm going to talk about something then called relative error. The idea of relative error is that I don't want to just look at the error itself, like how far off is the output. I want to look at how far off is the output compared to how far away are we in the input. So the ratio of these two things. And this idea of relative error and insisting that relative error be 0 is what's going to eliminate this obviously bad example. So here we go. Same function, 5x, right? There's the graph. Same ridiculous candidate, 3x. We know this is not what we want. We need a rule that will fail in this case so that we can eliminate this obviously mistaken candidate, right? So let's see if relative error does the job. Notice that relative error, this right here, you plug in the various things, and that relative error approaches 2, which is not 0. So if I require that relative error, not just error, relative error must go away, then as we want, this obviously bad approximation is discarded, as it should be. Everybody see the idea? All right, so that's all it is. That's all the, so vanishing relative error is a convenient term that people use to describe this. And here's how we write it down, and I know it's scary looking, but I don't want to get bogged down into details. But notice all this thing is, oh, I'm out of time. Oh my God. Okay, I'm sorry. I totally lost track of time. I guess we'll pick up here next time then. Okay, y'all have a good one. See you later.
I think I arrived after attendance.